Hello, hello. Good evening, afternoon, everyone. Today we're going to talk about periodic motion and torque. First, we'll deal with torque, the harder topic, and then we'll go back if we get and finish off with periodic motion. Okay. I just feel torque would be something that's more useful, especially since if you're looking at biomechanics, everywhere that you have a joint in your body, we're going to have some torque that can be applied. Okay. So let's start with torque. Torque is simply a force that causes rotation. So when you think of torque, you think of turning a bolt or screw or nut, right? But the main key points of torque are you're going to have a point of rotation, commonly referred to as a fulcrum or a pivot point. We're going to use some type of tool to create that rotation, usually a wrench. The distance from that point of rotation to where we're applying a force, let's say the force is being applied this direction, is commonly referred to as the lever arm / moment arm, denoted as some vector r. This is your force vector, and this is the angle at which it makes to the horizontal, okay? Theta. So torque is very analogous to force. So remember last week, that the sum of all the forces was equal to ma. Well, the sum of all the torques is equal to the rotational equivalent of mass, moment of inertia, and the angular equivalent of acceleration, alpha, or angular acceleration. So the rotational equivalents of each. I here is called the moment of inertia. And alpha is what we call angular acceleration. Okay. So it's acceleration in a circular path as we got it to rotate. So the way we define torque is simply the perpendicular force times that lever arm. So the way I think of it is we're only going to look for the perpendicular component, and the perpendicular component to my lever arm was the F sine of the angle, right? The vertical component. Remember last week when we talked about the horizontal component, when we only looked at work, the horizontal component of that work was the F cosine of the angle. For torque, it's F sine of the angle. So we write this as F sine of the angle, the perpendicular component, times lever arm. So torque is equal to F times R times the sine of the angle in between. Okay? And keep in mind that that angle is with respect to the horizontal. Okay? The units for torque is a Newton meter. That's the unit that we're going to be dealing with. Okay? Moment of inertia here? No. There's no square. Where's their square? This is an equal sign. I don't see how anything could else be mistaken for a square besides that equal sign. But yeah, so when we talk about moment of inertia, the arrow over the letters mean that they're vector terms. Week 1, when we talked about it, X had a vector notation arrow over it, Y had a vector notation arrow over it. So anytime you have a vector, that means that there's an arrow over it. Yes, vectors have both magnitude and direction. Moment of inertia is proportional to mass times the radius squared. So moment of inertia is proportional. That's what that symbol, that little looking like alpha symbol, is proportional to mass times some radius. There are 2 moments of inertia that you guys need to know. Angular acceleration is equal to the sum. So you know how like when we summed up all the forces for F is equal to ma after we added all the individual forces, torque itself is made up of perpendicular force times the lever arm. But when we sum them all up, we set them equal to a moment of inertia for that system times your angular acceleration. So just like you set it up, like sum of the forces is equal to ma, we write sum of the torques is equal to I alpha. Does that make sense? Cool. Could I repeat what the force is perpendicular to? Oh, it's perpendicular to my lever arm. Force is perpendicular to the lever arm. Hence why we're looking at this, right? Because if we chose this direction, that would have been parallel to the lever arm, but we're not caring about that. We did that last week, right? When we talk about work. That was parallel force times displacement. Here we're talking about perpendicular force times some lever arm, some point from where the pivot point is or the fulcrum is to where that force is acting. Angular acceleration. Are you talking about this alpha? Someone's asking me about what alpha means. Alpha means angular acceleration. That's acceleration in a circular path. Oh, this just means proportional. This one means proportional. Because it's not technically equal to, because each object has a different moment of inertia. Not the same thing. They're the same. The R's are the same. They're both lever arms. Same R. This is radius. Okay, I'll start a new slide. I'm going to do moment of inertia solely by itself, so let's not confuse anything, okay? Yeah, because if you think about it, when we're rotating, we have a radius at which we're rotating about. We call that the lever arm. Cool. Someone was wondering what R and R vector, are they interchangeable to each other? Yes, they are, right? Because when you rotate, if you think about it, I need to draw it out. This is the circle, right? And that R that we have for our lever arm is that radius of rotation that we have in our system. Okay, so 2 moments of inertia that we need to know. We need to know the disk and we need to know the hoop. So for the disk, it's a nice uniform, evenly distributed mass. For the hoop, all the mass is thinly on the edge of that piece. Okay? So the moment of inertia for a disk is equal to mr squared divided by 2. Moment of inertia for a hoop is equal to mr squared. M being the mass that they have on each of the hoops, and r being the distance that that thing is from the center. Okay. So these are the only two moments of inertia that I've seen the MCAT require students to know, hence why I'm going over it. Pretty much everything else you don't need to know, right? The reason being is most of the time when you're dealing with these rotation type systems, they're taking it at a point where it's in static equilibrium, where it's not moving, it's staying stationary at that point, okay? But when you deal with the human body, any joint that we have, whether it's the shoulder, the elbow, the wrist, the knee, the ankle, mass, M is mass. It's rotational mass. Moment of inertia is rotational mass. It's just how much inertia has when that object is beginning to rotate or spin. So when we're talking about torque today, we're talking about something that creates something to rotate, right? Spin. But these are the only two moments of inertia that you guys need to know. You need to know your disc and you need to know your hoop. There's a ton more, but we don't need to know them. You should thank your lucky stars. The other thing that we need to know, no. Moment of inertia is not the oppositional force. It's just the object's resistance to move, to change, right? Remember Newton's first law of inertia? So if an object is moving, it'll stay moving. If an object is stationary, it'll stay stationary. That's called the law of inertia. Same thing. If an object is spinning, it will want to continue spinning. But if an object is at rest, it's going to take a lot of force to get it to want to spin, to rotate. So it's really not oppositional. Oppositional is like kind of like friction. That's opposite, right? It's just the natural tendency of that object to do what it's normally doing. If it's resting, it wants to rest. If it's in motion, it wants to stay in motion. So whether it's rotating or going a translational motion, it's still staying in some type of motion. So inertia is tendency of an object to want to continue doing what it's doing. It's like being lazy, right? But in both cases, we have to put a force into it to get it to want to change. Okay, so now the next thing we need to know is the sign convention associated with your moments of inertia. There's such a thing as positive torque and negative torque. So realistically, torque is the cross product of force and the lever arm. And this is where the right-hand rule comes into play. So if we have a pivot point, there's our lever arm R, and we're going to apply a force. This force causes counterclockwise rotation. That's determined as positive torque or torque that is coming out of the beige. So this dot and X notation that I'm going to show you. So if you think of an arrow, if you see the tip of the arrow, that means it's coming at you. And if you see the feathers part of the arrow, it means it's going away from you. The other one is if we have clockwise rotation, right? A force that creates clockwise rotation. This is defined as negative torque or torque that is going away from you, okay? So what we need to see, let me turn on my camera. So if you point your fingers, so if we're using our right hand, first of all, we're using right hand rule to determine torque. Point your fingers in the direction of the lever arm, curl them in the direction of the force. So what you notice is your thumb, which is the direction of torque, is pointing right at you, right? Or out of the page. Does that make sense? So if you're doing it along your paper, you're pointing your fingers along the lever arm R, you curl them in the direction of the force, for the top one, counterclockwise, right? Your thumb is pointing at you, right? Or out of the page or out of the paper or out of the board. Now, if you do the other case where you point your fingers in the direction of the lever arm and then curl them clockwise, you notice that your thumb is pointing into the board or into the paper. Okay, so this is going away because it's going counterclockwise. This is going clockwise. Notice that the thumb is going right at you. Okay, so that's what that X means. That's just the direction of torque. The reason that you want to do this is because when you actually have things that are in motion, think of like any type of running that you do, it's a force that we're applying based off of some lever arm or some distance from a pivot point, right? Either your knee, your ankle, right? Or even your hip, right? When you're, pumping your legs. Those are all things that are going to get you some type of torque, okay? But you need to know the direction associated with it as that force is being applied to your system. So you know what's positive torque, negative torque, so that when we do the summation of it, you can either get a positive or negative angular acceleration. This is the direction. So if we think of the arrow, like I said, this is the feathers part of the arrow, this is the X, and if you see the tip of the arrow, that's the dot. Cool? That's what the dot and the X stand for. So if you see the feathers, it's going away from you, and if you see the dot, it means it's coming at you. Cool? That's what that dot and X notation stands for. We'll see this dot and X notation again when we talk about magnetic fields and electric fields. So don't be surprised. Just means it's direction. What do you mean opposite of thumb? Yes, that's why we use the right hand rule. Correct. So, well, if you think about it, it's direction of the thumb. If the thumb is going away from you, right, aren't you going to see the feathers part of the arrow? And if you see the thumb is pointing at you, that means the tip, right? Don't you point at someone? That means it's going that way. So I don't know why it's like clockwise, his thumb is away from you. So you might be doing right hand rule wrong if you're getting your thumb pointing at you when you're doing a clockwise rotation. Sure. Let's go over it again. Point your fingers in the direction of the lever arm. Sorry. So point your fingers in the direction of the lever arm. Is my hand on camera? I can't see myself. Sorry. Okay, there it is. Curl them in the direction of the force. So where's my thumb pointing? Towards me, right? Because it's all relative to the person using the right hand rule. It should be towards you, right? So that means that's where the dot is. So point your fingers in direction of the lever arm, curl them in direction of the force. So counterclockwise rotation, this is counterclockwise to me. When I'm looking at myself, this is counterclockwise. So my thumb is pointing at me, which is why it's a dot. Now the other case is if my fingers are going this way and now I'm going to create clockwise rotation. So this is clockwise rotation for me. My thumb is pointing away from me, right? It's this, my hand now is going away from me. It's going towards the camera. So away from me is the X. The fingers start where the star is. You move it along R, and then you curl them in the direction of the F. Yes. So if you think about it, here's the star, right? And then I'm going to rotate my fingers because this is my lever arm, and my force is pushing this way, right? It's pushing up to get it to want to rotate. Does that make sense now? Good. Right-hand rule is very important, like Jonathan said. So we need to get this right. That's why I'm spending a little bit more time on this. Things that are a little bit less important, I'll try to not spend so much time on it, okay? But right-hand rule is pretty important, especially when you're trying to figure out what direction the torque is pointing, okay? Okay, so now that we know the direction of torque, positive and negative, right? We can do our summation of torques. But let's look at the type of torque equilibrium problems that we're going to get. So the cool thing about all these torque problems that we're going to do, we're going to always be in some state of equilibrium. So when we say equilibrium, we mean no angular acceleration or linear acceleration. Remember, these are all vector quantities, but we can have constant linear velocities and angular velocities, okay? So the first type of equilibrium that you guys need to know is when the summation of all the forces is equal to 0. Last week we called this translational equilibrium. This is all our static type problems that we did last week. Okay. The second is the summation of torques. So when the summation of torques is equal to 0, it's omega. It's not W. Omega is the symbol for angular velocity, or variable for angular velocity. Summation of torques being equal 0, we're in what we call rotational equilibrium. Okay. The third state of equilibrium we've already discussed. That's if velocity is equal to 0 and angular velocity is equal to 0, right? Then we have static equilibrium. Okay, so going back to translational equilibrium, keep in mind that even though acceleration is equal to 0, you can be moving at a constant velocity, right? And for rotational equilibrium, if the net torque is equal to 0, we can be rotating in a constant angular velocity, okay? So just keep that in mind. Just because the accelerations, linear and rotational or angular, are 0 doesn't mean that you're completely still. Sure. In translational equilibrium, you may be completely stopped or you can be moving at a constant velocity. In rotational equilibrium, you could be stopped or you may be rotating at a constant angular velocity. Does that make sense? Cool. And then static equilibrium, we've discussed. Everything staying still. Okay? So let's hit some problems for thought. Get you guys thinking. So first problem, we'll call this problem 1A. We have a rod of length 2L. We're going to apply a force of 10 newtons on one side, apply a force of 10 newtons on the other side. What is the net force that I have acting here? And what is the net torque that I have acting here? Good Lord, we'll say net. Units for force should be in newtons. Units for torque should be in Newton meters. So L. The length is 2L. So let's get you guys thinking. What's my net force? What's my net torque? So we have a force on one end pointing down, on the far right end, it's pointing up. On the left end, it's pointing down. On the other, it's pointing up. So are we going to have a net force on here? Or are we going to have a net torque on here? And then what type of equilibrium do we have in this scenario? Apply what we just learned for torque, and you already should know what we talk about forces. So net forces is like up minus down, right minus left, right? And then for torques, it's clockwise versus counterclockwise, or counterclockwise rotation versus clockwise rotation, right? Counterclockwise is positive, clockwise is negative. Close Aditya. Try again with torque. Figure out where the point of pivot point is, or the point of rotation. Yeah, and you forgot to include the length, because it's force times lever arm, force times lever arm. Okay. Net force, that should be self-explanatory at this point. If we're not, that's what office hours are for. I sent you guys all an email with my office hour link for Thursday, and we'll have office hours after class today if class doesn't go over. Okay. So if you have questions about how to understand net force, net torque, work, energy, and translational motion, and all the stuff that we talked about before with physics, feel free to come to office hours. So we have a downward force, which is -10, and an upward force, which is +10, right? So my net force should be 0 newtons. So the question I asked Aditya was, where's my pivot point? And this ended up being my pivot point, right? This is the point of rotation at which you're going to be pushing. So if you don't believe me, put your pencil down that you're writing with, or your stylus or whatever, and push on either end with your fingers with even force, right? And it's going to rotate about the center of your pencil or pen, right? So then this length is L and this length is L, right? And how do we determine torque? Perpendicular force times lever arm, perpendicular force times lever arm. Yeah, it's because it's 10 in both directions, yes. If it was uneven, right, one would be rotating and then you would have rotational motion as well. But right now I'm just trying to get you guys thinking about torque type problems that are fairly balanced, right? So this force, does that cause clockwise or counterclockwise rotation? Good, counterclockwise. This force, does this counterclockwise or clockwise rotation? Is this clockwise? Counterclockwise. Right? So they're both positive. So since they're causing the same path of rotation, they get added to each other, right? That's why it's 20 L Newton meters. So what type of equilibrium are we in? Translational, rotational, or static? Good. Net force is equal to 0. We have translational equilibrium. Cool. So let's change it up. These are just some problems for thought. So I'm going to call this 1B. What's going to happen is I'm going to change the direction of my arrow. So instead of pointing down on the left-hand side, it's going to be pointing up. Same 10 Newton force. So my question to you is, what is the net force? What is the net torque? Correct. It's translational because net force is equal to 0. Good job, Monica. So this is 1B. We have 10 newtons on one side and 10 newtons on the other side. Sorry, I accidentally erased the 1 from the 10. Brooke says 20 and 10 and 0. Brooke would not be wrong. But let's give everyone a quick chance to think about it, right? We have a 10 Newton force on the left that's pointing up and another 10 Newton force on the right that's pointing up. Imagine if you have your pencil and push with it equally on either side, right? You notice that your pencil goes up, right? Or up on the border on the page. We're assuming it's like on a table or something. Right? Gravity is being canceled out by normal force. So net force is going to be 10 plus 10, which is 20 newtons. Net torque, so this is going to cause this type of rotation, and this is going to cause that type of rotation, right? Same pivot point. So this is counter. Okay, so this one, is that clockwise or counterclockwise? Look at the pivot point and look at the rotation. This is going to be clockwise. This is going to be negative 10L, right? Newton meters. This one on the right-hand side is going to be counterclockwise. Think about it. If your pivot point's at the center, one's pushing, the other one's pushing, right? It's going to cause it. So imagine if you push it by itself, Jonathan. You'll see it. Put your pencil down, try it out. It's really quick. Physics is one of those things you gotta like, you lived it, right? Like you can actually experiment with it. The cool thing about the first half of physics, which is all mechanics, these are things you can apply and do every day, right? It's all right. We all have one of those days. It's Mondays. Usually you turn your brain off for the weekend, goes on a vacation, needs like a, you know, some paddles to bring it back to life again. Right? So let's resuscitate it now so the week goes better. No worries. Everyone has an off day. So negative 10L Newton meters plus positive 10L Newton meters gives us 0 Newton meters, like Brooke said. Okay. So what type of equilibrium are we in? Translational, rotational, or static? Very good, Aditya. We're in rotational because the sum of all the torques is equal to 0. Yeah, we would always include L, right? Because isn't it perpendicular force times lever arm is equal to torque? Oh yeah, you're right. It's 0L. But yes, 0 times any length, right, is 0. So that's why I didn't write the L. Right? Because L would confuse people and they thought it would be a variable. But normally you would have some length to this rod, right? And then you would have to include that number with it if there was actual net torque. Okay? All right. Let's change it up a little bit again. So instead of having just this free rod that's able to move, I'm going to take a nail and really nail it to the table. or the wall, right there, right? So if there's a nail through your pen or your pencil now that's holding it in to your table, and you push up on either end with 10 newtons, what's my net force? What's my net torque? Good. Everyone's beginning to see it, right? This would be question 1C. Sorry. Cool. If you think about it, there's 0 and 0. So there's 10 to 20 newtons going up, but at the nail, there's 20 newtons going down, right? Otherwise, the nail would be doing a really piss poor job of being a nail, right? The whole point of a nail is to keep something in place. Oh, man. You guys and your puns. Like at my age, we call them dad jokes. But yeah. And then net torque, same thing again. This is counterclockwise. This is clockwise, and they're going to cancel each other out. Negative 10L plus positive 10L gives me 0 net. So what type of equilibrium are we in here? Translational, rotational, or static? Very good, right? Now we're completely stationary, right? Nothing is moving. So the reason I did this whole exercise is, one, it forces you to practice how to use the torque equation, perpendicular force times lever arm. Goes back and reviews our forces from that we talked about last week, our net forces, right? And adding them up with each other. And last but not least, understanding your equilibriums. There was a question, what would the torque be if there was a nail in question 1A? In question 1A, the torque would still be the same. It will be 20 L Newton meters, right? Since it pivots about the center, it didn't change the pivot point with the nail there. Correct. Static means no motion, completely still, like the dead. It depends on how old that nail is. Someone says, can it rotate with the nail in it? In that case, if you think about it, where's the nail? The nail's at the pivot point, right? So what's the lever arm on the nail? There's no lever arm, so therefore no torque, right? If you think about it, to answer that question, where do you put the doorknob to a door? At the where the hinges are, or as far away from the hinges as possible? Right? Think of your door. Everyone has a door in their house, in a room, a car, right? Where do you put the handle to open the door? Is it at where the hinges are, where the pivot point is, where the fulcrum is? Or is it as far away from it as possible? What would the F net and net torque look like if the nail was not placed in the center of the lever arm? Haha! Then you would have different torques, right? And then you would have a net torque in that system, right? Yeah, you think about it, like no one ever puts the doorknob right next to the hinge, right? And try imagining opening a door with your, like your doorknob, or try pushing it on a door close to the hinge. It's near impossible. Okay, so torque is perpendicular force times lever arm, right? If we're at, this is the force of 20 newtons, right? What's the lever arm? How do we define lever arm? Lever arm is the distance from the pivot point to where the force is acting. But if the force is acting at the pivot point, is there a torque? What's R? Exactly, right? R is 0, right? If we have 0 net lever arm, there will be no torque. So that means that force that we push at the pivot point creates no rotation, right? Remember, what is torque? Torque is a force that creates rotation. Now, if we push that force at the pivot point, we won't ever have rotation. So that's why it doesn't add to the net torque, even though there's a force at the nail. Good question. That's why I use the door example, right? No one ever puts a doorknob right where the hinge is. Right? Yeah. The reason being, right? Like if you're getting your arm to rotate, right? Like let's say you're trying to lift someone's arm to rotate because they like might have torn their rotator cuff or whatever, right? Do you grab it right at the shoulder and then move it from there? No. You grab them by the furthest end, like near the elbow, and then you slowly move their arm up. Yes, greater torque. Yay. Of course, you want to be as far away, right? Because torque is both the force and the lever arm. So the farther your lever arm is, the greater that torque can be, right? And you don't even have to put that much force in to create that, okay? So let's take a look at an example using a basic seesaw. This is like your typical seesaw problem. We'll call this question number 2, okay? And we can see when they're not equal. So we have your typical seesaw. There is a single person on one end. They weigh about 500 newtons. On the other end, there's a couple. They have couple weight. They weigh around 1,500 newtons. Definitely not as in shape as the single person. Given that this whole seesaw is 10 meters long, I want to know what distance away from the single person is the fulcrum placed. So let's say this is the fulcrum. I want to know this distance d so that this system is in static equilibrium. If you think that couple weight is false, go look at a picture of your parents before they were married and a picture of them now. Everyone looks thinner on their wedding day. 100%. Exactly. Because you think about it, right? Think about it. What do you do when you're a couple? You eat good, you cuddle, you watch movies, right? Date night, eat French food, fancy food, richer food, right? What do you do when you're single? You work out, you try to look good so you can, find a mate. I know. I've been there, man. I've been there. Everyone will find their significant other. Trust me. It's like it's natural. It'll come. It'll come when you least expect it. So the question's asking, what distance away from the single person should this beam center thing, the fulcrum, be placed so that this seesaw doesn't move? It's balanced. Oh yeah, I remember that. I when I was studying for the MCAT. Sorry, someone commented that like they would eat snacks all day. I remember that when I was studying for the MCAT, I had those Costco bags of gummy worms. I literally, in a study session from 8 in the morning to 8 at night, I ate a 5-pound bag of gummy worms. No joke. Oh yeah, it was just you munch, you munch, and then I was like, oh my god, I didn't eat dinner, I didn't eat lunch, I didn't eat breakfast. All I ate was gummy worms, and I felt horrible. But yeah, trust me, we've all been there. Yep. Yeah, I feel like 2% gummy worm. I'm quite squishy. It's all right. If you're still single, you're gonna go back and work out. It's only the couples that are screwed. Right after the MCAT's over, you're gonna go and hit the gym. Then you need to find another single person that doesn't work out. Yep, squishy. Hey, some people like squishy. Some people like buff. You don't know. That's why I said there's someone for everyone out there. Yeah, sadly, yes. Someone quoted that, will I be 100 times more gummy worm like when I'm in a relationship? Probably, yeah. Sadly, yes. Okay, so couple weight aside, let's see if we can do this problem. Okay. So we have the okay. We have answers. Let's look at some of the answers. People were privately messaging me. We got 5 meters, 7.5 meters, 8 meters, 2.5 meters. Okay. Enter choice A, B, C, and D, respectively. Okay. So let's take this. So this is going down, and this is going down, right? Their weights are always going down. So which is causing clockwise, which is causing counterclockwise? So is the single person clockwise or counterclockwise? Good. Counterclockwise. So single person is 500 times D. So perpendicular force times lever arm. That means the couple is clockwise, right? Not saying that being a couple is bad. They're just negative in this case. This just turned out that way, okay? So minus 1500 times the distance here is what? 10 minus D. Okay? Perpendicular force times lever arm, right? That's equal to I alpha. But since it's in static equilibrium, we know that angular acceleration is 0. Okay? So we get 500D minus 15,000 plus 1500D is equal to 0. Yeah, sum of net torques, right? Aren't we summing these? Isn't that what we just did? This is what it's equal to. I just substituted in for the equation, right? So you end up with 2000D is equal to 15,000. Divide out the thousands. What's 15 divided by 2? 7.5 meters. For those who got that, very good job. Yeah. Amazing. You're doing physics. Yes, some people are more excited about it than others, but yes, you're doing it, right? All we're doing, perpendicular force times lever arm, perpendicular force. Oh, well, the whole length was 10, Sophie, and if this distance from the pivot point to where the single person is D, then you subtract it, right? So it's 10 minus D is this distance. Yeah, it's because I stipulated it was 10. And then I just chose, you could have done you could have done D over here and then 10 minus D, and then you had to find your whatever your answer was, and you had to take 10 minus that answer, right? Another way of thinking about it is if the single person only has 1/4 of the total weight being 2,000, and the couple had 3/4 of the total weight, the single person is going to need 3/4 of the length to equate with the 1/4 of the length for the couple, right? Because technically, what is this? This is a pan balance, right? You guys do this in chem lab or bio lab even all the time. You do a pan balance weighing one versus the other, right? The seesaw problem that we have here, this is your typical pan balance that you do in lab. Does that make sense? Okay. Good job, good job. Let's make it a little harder. So Josh, Todd, and I have been talking, and not like there's students outside, but we wanted to hang some signage up for Berkeley Review. So that's a building. Here's a rod or a beam that can hold up a sign. We're going to use Josh's artistic abilities. He's a wonderful artist, by the way. I don't know if he's like drawn you guys anything cool yet, but he's a wonderful artist. And then we're going to hang it up by a cable that makes an angle of 30 degrees to the horizontal. I'm going to tell you that the weight of the beam is 500 newtons, and the weight of the sign is 1,000 newtons. I want to know what is the tension in the cable. So I want to find this tension. The TBR thing is the sign, and the beam is that rod that's holding it there. So weight of the sign is 1,000 newtons, and weight of the beam is 500 newtons. The length of the rod is some length L. It doesn't matter. Key to the problem is figuring out where the pivot point is. I'll leave that up to you guys. Especially the people who got it right the last problem. We're trying to hang a sign up. The sign weighs 1,000 newtons, and then the beam that's holding the sign weighs 500. And there's a cable that is attached at the end of the beam, right? I want to find the tension in that cable that'll hold the system up where it's attached 30 degrees above the horizontal. That's not RT, it's just an arrow with tension. Oh yeah, it does. Michaela, why would I ever give you a question that isn't applying what I taught you that day or something I taught you in the past? What do? We break all the vectors into components, or the ones that we need to, right? So that they're perpendicular or parallel to the lever arm. The lever arm being the beam, right? We're not moving the beam. So let's get some answers. Some answers are streaming in. Okay, if we're hanging up the sign, should anything be moving? There you go. That should answer the question. Correct. Static equilibrium. That is the goal. We don't want lawsuits here. We're not going to law school. This isn't teaching the LSATs. Sorry. I hope so. I hope so, Jonathan. Okay, let's get started. People have sent in answers. I got 1,500 newtons. I got 1,000 newtons. I got 250. I got 1,250. Jesus, 3,000. 2,500. I think that's it. Oh, 750. Cool. And no, we're not playing the prices right. 1 over doesn't make it better. One person was like 1,001. Okay, so let's take a look. First of all, where's the pivot point? This is the first thing that you should be doing at any type of rotation problem. Where's my pivot point, right? Imagine putting a pencil against the wall, right? Where's it gonna rotate from the beam? Right here. Yep, at the point where it's touching the wall is where the pivot point is going to be. Correct. So now let's just draw it. Let's imagine that we draw it without anything else, right? On this end, we have a weight of the beam. Then we have the weight of the sign. Yeah, once we see that, right? That's why I was asking people. A lot of people were like, "Oh my God, it's so much easier now that you showed me where the pivot point is." Like, I was like, first question I asked you guys, the key to this problem, where's my pivot point? And then we have tension, right? Okay, so if you think about it, right? Normally, if you just put a pencil and rest it against the wall and you let it go, what's going to happen? It's going to rotate. So here, let me show you on the camera. So look, this is the wall. Think of my hand as the wall, right? What's going to happen if I let go on this end? It's going to do this, right? So you think about it, that's rotation right now. So what we're doing is we're trying to hold it up by a force with the cable pushing up this way. But then there's the weight of the beam, which is this pencil, plus the weight of the sign that's hanging on here, right? So now we have to decompose that tension into a T sine of 30 and T cosine of 30. So we'll turn off the camera so you guys don't have to see my face where I'm writing this. It'll be way too close. I already have that cup of weight. I don't need you guys to see it. Okay. The other thing, that's not too bad. Big forehead. The other thing, oh, someone was asking, how do I know that I can break up tension? If you think about it, tension can be broken up this way and this way, right? And this is theta, right? So this was T, this is T sine, because this is the opposite side, and T cosine, because this is the adjacent side that we're using from SOHCAHTOA. Does that answer your question? Oh, vectors. So the cool thing about vectors, you can move them anywhere in 2D space or 3D space, but they still have the same meaning. As long as they're acting from where the original force was, it should be fine. So whether I draw this tension here or move it here, it's the same thing. Cool. Yes. No one ever told you that about vectors, huh? Vectors mean the same thing as long as they act from the same original point. Yeah. That's the cool thing about vectors. So they have the same meaning. Okay. So now we know how to decompose vectors again. The other thing that there's two forces that are hidden here that I didn't tell you. The first is, look at that. We're resting on something. So we have a normal force. The wall is pushing back on our beam, right? And we're resting against the wall. And if this was to fall, it would have slide down, right? So that means there has to be friction acting on that wall. Yep. Friction works too. Jonathan got too excited. He forgot the F. So if you think about it, these are all the forces acting on that problem. So we did it with summation of forces. Let's do some of the forces in the X. We have normal force minus T cosine of 30 is equal to 0 because it's not moving horizontally. Otherwise, we have to pay the building manager something, right? The other one, some of the forces in the Y. We have up minus down, right? So the up force arrows are T sine of 30 plus mu s times n minus weight of the beam minus weight of the sign, right? I'm just abbreviating S and B for short, okay? Not writing out the whole sign and beam. That's equal to 0. So if we did this using forces and what we learned last week, how many unknowns do we have? We don't know normal force, we don't know coefficient of friction, and we don't know tension. So 2 equations, but we have 3 unknowns. Can we solve that system of linear equations? Yes, no, maybe so? Remember, system of linear equations only work when you have the same number of unknowns as the same number of equations you have. Yes, we have too many unknowns. Good. Too many unknowns means they're pointed down. The reason that the weight of the beam and the weight of the sign are both negative is they're both pointing down, right? Isn't down negative? Isn't left negative? Up minus down, right minus left. We're good on notation for direction. Okay. So this is our summation of forces. This is literally what we did last week, right? And it's not going to work for us because we don't know things, right? We don't know the wall force. We don't know that normal force. We don't know the friction on the wall. No good. No bueno. Muy mal, right? So we got to use what we learned today. Summation of torques. And we know our pivot point. So it escalated quickly because you went from being summation of forces to summation of torques. Something that we've just been going and doing this whole almost an hour and 6 minutes now. So let's take a look. So we're going to look at things that create counterclockwise versus clockwise, right? So given that this is our pivot point, just because we use the scary word of torque, right? The T word. Don't worry. We're going to use what we've been doing this whole time, right? Counterclockwise minus clockwise equals 0, right? So which force is going to create counterclockwise rotation? In terms of the up arrows. Okay, think about it. So weight of the beam, that's going to cause your force to go this way, right? If this hand is going this way, is that clockwise or counterclockwise? That's clockwise. So be careful. Weight of the beam is clockwise rotation. Counterclockwise rotation, like what Brooke and Michaela said, were tension. Good. So we only want the perpendicular component of tension. The parallel component does us no good. So perpendicular component of tension, T sine of 30 times the whole length, L, right? Because perpendicular force times lever arm minus weight of the beam. The lever arm here is L over 2 because it's at the midpoint of the beam is where the weight would act. Minus weight of the sine times L is equal to I alpha, but that's equal to 0, right? So we have tension sine of 30 minus times L minus weight of the beam times L over 2 minus weight of the sine times L. Oh, wait, we have another perpendicular force, the weight of friction. But what's the lever arm for that torque? The force is acting right at the pivot point. Correct, Brooke. Sophie, I was looking at you. So, if we were in class, I've been looking at you. Okay, good. You thought it. Awesome. Awesome. So now that we know that, sure. The last part is, since the friction is at the point of rotation, it has 0 lever arm. Typically, there's usually some type of force from the wall, and the force isn't usually just horizontal. It's usually at an angle, Jonathan. So you can always decompose that force. At any pivot point in real life, that's typically the case because there's something that's rotating or it's touching, right? But yeah, in engineering terms, in real life terms, yes, but in ideal physics terms, no, to answer that question succinctly. Correct. L is 0, therefore there's no pivot point, so therefore no lever arm, therefore no torque. That's why we don't include it in the summation of torques. Okay? So let's do our math. Plug in the numbers, right? Sorry. I didn't erase it. It's still there. I would have been very, very mad. Good Lord. Stop making new pages. So I'm going to write it over here. So T times 1/2 times L is equal to weight of the beam, which is 500 divided by 2, so it's 250 L, plus weight of the sign, which is 1,000 L. Let's get rid of all the L's because every term has an L in it. All I did was just add it to the other side. So tension times 1/2 is equal to 1250. So tension is equal to what? 2,500 newtons. Divided by 2 right here. Yeah. Remember, the lever arm and where the force of a weight of an object is always at the center of that object. And for the beam, it's at the center of the thing. So therefore, the lever arm is half of that length. That's why it's L over 2 for the lever arm. That's why it's 250, not 500. So be careful. So you're probably thinking that this problem makes no sense and when the hell are we ever going to hang a sign up, right? Well, instead of calling that beam, let's call this the forearm. Instead of calling it the wall, let's call this the elbow, because that's our pivot point now. And instead of calling it tension, let's call these ligaments that are being attached here. Does this problem seem more applicable now to medical science? So instead of having, oh yeah, right? So this is your backpack that you're holding, right? This is some weight. This is your groceries, right? That you're holding on your arm. So instead of the weight of the sign, it's the weight of your backpack or the groceries that you're carrying, right? Or your books, right? Instead of a beam, it's your forearm. Instead of a tension in the cable, it's the tension in the ligaments that you have, right? Instead of a pivot point against a wall, we call that the elbow. And instead of the wall, this is your humerus, right? Is this an applicable problem now? So the reason that I want to spend this time going over torque, and we're going a little bit over that 1 hour mark, that I like to break up for evenly for the chapters. How I got the variables in the sum of the torques again? All I'm doing is just doing this. I took my perpendicular force times that lever arm. Perpendicular force times lever arm, perpendicular force times lever arm. Someone was asking me how I got the summation of torques and how I got all the equations. So the lever arm here is L over 2. The lever arm all the way to here is just some length L, right? So from the distance of the pivot point to where that force is acting is my lever arm. Okay? Awesome. So this becomes a very applicable problem, and it's something that you're going to have to deal with, right? So every time you think about it, anytime that you have a point of rotation in the body, a joint, you're going to have to deal with torque, right? Think of your elbow, your wrist, your ankle, your knee, your hip, right? You have torque on your spine, right? That's why if you have bad posture and your weight is over your spine, it's going to get it to bend down because gravity is pulling that spine down, and it's going to cause it to rotate. That's how people get scoliosis, right? And their back is all effed up. But if you align your back properly and all your weight is supported, then you don't have like that arched back, right? No one wants to look like Mr. Burns. But yeah, think about it. All the biomechanics that you're going to be dealing with. Yeah, well, we're all getting shorter, Jonathan. No one's getting taller, right? After 25, it's just all downhill. You're not growing vertically anymore. I know. I wanted to be a basketball player. I ended up not being like, 6'8". So I, have to live with that. But yes, back problems, something you can avoid though. Becoming short, something you cannot avoid. Yep, exactly. So when we're studying, right, make sure that you have correct posture so that your weight isn't leaning over so that it'll cause your back to arch, right? Because then you're creating torque on your back. So these are the things you can do and that you apply every day, but you don't even think about it, right? You do this subconsciously. Oh, wow. Okay. Too much torque. Exactly. All these things that we're talking about in mechanics, we can apply it to what we do every day, from opening a door to basically lifting your leg up, right? Or lifting your foot to move and walk. We're using torque every day, all the time, you know? So this is why it's super important because all those biomechanics, they'll have like soccer players or kickers kicking an object, planting their foot down and swinging their leg through, and then you're gonna have to figure out how much torque they got from the rotation in their knee. And they have those practical application type problems on Next Step and your AMC type practice tests, and you see this all the time. So this is why torque is important because it comes up, and any type of rotation that you have in the body, it comes up again. Okay, so we got to make sure that we have this lock on lock. Okay, no joke. Okay, so now we're done with torque. Let's talk about periodic motion. So periodic motion is the movement of things that repeat themselves. So let's do some quick vocab for periodic motion. Let's define what is a period. Do you know it as capital T for period? It's simply the time it takes to complete one cycle. So when we say one period of something, like, you know, a year for us, that's one period, that's one cycle of the Earth orbiting the sun. So it's the time it takes to complete one cycle, a period. The other thing we need to know is the frequency. How often do we do these periods? So frequency, you know, that's little f, lowercase f, is 1 over the period, and it simply states how many cycles completed per second. The units for period is in seconds. The unit for frequency is in inverse seconds, otherwise known as a hertz, denoted as capital H, lowercase z. Okay? So this tells you how many cycles we have completed per second. And last but not least, we have angular frequency, denoted as omega. It's simply 2 pi times the linear frequency, or 2 pi divided by the period. The units for angular frequency is in radians per second. Okay? So instead of having the thing repeat up and down, up and down, up and down in like a wave type motion, we can think of it as going around in a circle type motion. That's why we're translating linear frequency to angular frequency, right? So what periodic motion does is it models what we did, let's say, in position versus time. Starts at some amplitude, goes down, comes back up, so on and so forth, right? And so the typical, sure. Cool. So if you think about it, this is your typical sinusoid type graph, right? where the equation is equal to some amplitude times the cosine, it's not sine, cosine graph, omega t, right? And the velocity would have been derivative cosine is negative sine, omega t, and your acceleration would have been negative a omega squared cosine omega t. The most important part is that acceleration is equal to the negative times omega squared times the displacement vector. Okay, and so we're going to use this later to model real life things that are actually occurring. So when we say that things are traveling in a periodic motion, we're using a mathematical model to actually show that's where its type of motion is existing. Okay, so there's two types of systems that we need to know that are oscillating and repeating themselves. Okay, so the first is your oscillating blocks or mass in a spring. So we talked about these mass on a spring type systems, right? We talked about, sure. The key is that acceleration negative omega squared times displacement, and displacement was this a cosine omega t. Okay, that's the key, because we're going to relate it back in a second. So for this oscillating block system, remember this was your compressed spring system or your stretch spring system, and this was somewhere in between when it was at rest by itself and we didn't move it. This was some positive x displacement. This was some negative x displacement that we had in our system, right? But the equation governing that was F was equal to negative kx, right? Hooke's law for spring force. And we know that that's equal to mass times acceleration. If we write it out for acceleration, we get a negative k over m times x. Look at that. It's a negative, and acceleration is equal to a negative times something times x, right? We saw that earlier. That was negative omega squared times x, or angular frequency. So we can say that, look, this k over m term is exactly that angular frequency that we got from our mathematical model that we had earlier. Because this pendulum goes back and forth, back and forth, back and forth, very much like that displacement graph as a function of time looks, right? So we can state then that omega is equal to the square root of k over m, and that's equal to 2 pi times the linear frequency. So linear frequency is 1 over 2 pi times the square root of k over m. And the period is the reciprocal of that. That's 2 pi times the square root of m over k. Okay? So this is your period and frequency for a mass on a spring type system. Acceleration negative, displacement, and this thing is the same as this thing. Okay? That's how you can equate them to each other. No, we do not need to know the derivation, but it's good to know where it comes from, right? Especially since this is like the first time you guys are all seeing this for some of you. All good. Now, let's take a look with your equilibrium associated with springs. And this is associated with the energy associated with springs as well. So if we look at, so we're looking at conservation of energy with springs. Last time we didn't get a chance to do any of those work energy type problems. Well, since you're going to be dealing with springs, a lot of these things come back into play. So, if we think about it, energy as a function of displacement, say this is x is equal to 0, right? One energy graph would look like this. And the other energy graph would look like that, right? We know that potential energy is 1/2 kx squared. So that's definitely here. That's when potential energy is at a maximum. And we know that that converts into kinetic energy, 1/2 mv squared. So the concave down graph would be the kinetic energy type graph in your system. Okay. Keep in mind that when we're at a maximum displacement, velocity is equal to 0, and acceleration is at a relative max, and the restoring force or the spring force is at a relative maximum, right? Negative kx is maximum displacement as possible. And when we're at equilibrium, restoring, that's an R. Let's call it S spring so it's consistent, okay? Restoring force, spring force, same thing. So when we're at equilibrium for displacement, this is at x is equal to 0, we notice that velocity is at a relative maximum because all that potential energy gets converted into kinetic energy. And at that specific point, acceleration is equal to 0, and that leaves your spring force or your restoring force equal to 0 as well. Okay? So just know that's what's happening. So you're converting from one energy state to the next energy state, respectively, right? And anywhere in between, you have both kinetic energy plus potential energy. All right. Let's give you a quick question. Let's say we have, so this is question number 4. Say we have a spring. We stretched it out. And it has some displacement of A. Some over here, this is where equilibrium was before we stretched it out. And so as this thing is coming back at x is equal to A over 2, I want to know what fraction of total energy is in kinetic energy when the mass is at x is equal to A over 2. So think of what we start with and what energies we have when x is at A over 2. And then to find the fraction, we take the partial divided by the total energy that we started with, okay? We're just still using conservation of energy, right? Except now we're doing it with springs. Elastic potential and kinetic energy. apologize if you guys are hearing the creakiness of my chair. That just means that there's friction at the pivot point. Can be easily solved with some WD-40, but I haven't had time to do that. Sorry. So what fraction of total energy is in the kinetic energy when mass is at x is equal to a over 2? Equilibrium is when x is equal to 0. All right, so let's take a look. Answer choices I got, by the way, were 1/2, 1/4, 3/4, 4/5. A, B, C, D, respectively, right? So let's erase this real quick. So initially, what energy states did we start with? Are we in motion at this point? Yeah, we have all potential. And then at this point, we have potential plus kinetic, right? So PE initial is equal to PE plus kinetic. So 1/2 KA squared is equal to 1/2 KA over 2 quantity squared plus kinetic, right? So kinetic energy is 1/2 KA squared minus 1/8 KA squared, which leaves us with 3/8 KA squared, right? 1/2 is 4/8. 4/8 minus 1/8 gives us 3/8. And then that tells us the amount of kinetic energy we have at that point. But that's not the fraction, right? So we have, in order to get the total energy, what's our total energy? It's this amount, right? What we started with. So the fraction would have been 3/8 KA squared divided by 1/2 KA squared. KA squareds would have gone away. You would have ended up with 3/4 in terms of total energy. Was in kinetic at that point. If we look at it halfway back between x and 0, that's what it looks like, right? This is kinetic up here. This is potential down here. Make sense? Any questions? Which 1/2? This 1/2? I found the common denominator. Right? Common denominator is 8. So this is 4/8. 4/8 minus 1/8 gives us 3/8. I didn't multiply it by 3/8. That was the end result when I did my subtraction. Right? 1/2 is the same thing as rewriting it as 4/8 by multiplying top and bottom by 4.
No, I meant like when you like you went from 3/8 and then said something about 1/2 k squared and then got 3/4.
Oh, yeah.
I just
Fraction, right? Right here.
yeah.
So what's 3/8 divided by 1/2?
3/4. But I was just wondering, why did you do that?
Because this is the part, this is the kinetic energy, this is total energy, right? So don't you take the part of the energy, in this case the kinetic, divided by the total to get the fraction of total energy?
Okay.
That's what we're looking for.
Okay.
I plugged it into the equation, 1/2 kx squared. X in this case was a over 2. A squared divided by 4, so 1/2 times 1/4 gives us 1/8. Cool. Yes, k is a constant. They would have to give it to you, but most of the time they just leave it as k. And as you can see, the constant was the same, so we can cancel out. Conservation of energy is probably the fastest way possible when you're doing these types of questions. Someone was asking me, how do we avoid spending so much time on it? We're just doing conservation of energy. Well, isn't kinetic energy the difference in the potential energies? And the only way to cancel it out is if I left it in Ka squared form. Because I don't know what kinetic energy is at that point, or the velocity of that object is at that point. Right? Cool. So we're using that conservation of energy that we talked about last week, and they'll give it to you in these types of questions, okay? When we're dealing with our periodic motion. And it comes back. It's all cumulative, right? Everything that we talked about from week 1, week 2, now we're on week 3. It's all going to be cumulative with each other, okay? So let's say we have an object colliding with a spring. So we have an object of mass m1 traveling at a velocity v naught. It is then going to collide with an object of mass m2 whose initial velocity is equal to 0, which is also attached to a spring that is at rest right now. And that spring has some spring constant k. I want to know, 1, what is the frequency after collision? And I'm going to tell you that these objects are made out of clay, so that when they collide, they're going to stick with each other. And the second question is, what is the maximum displacement of the spring? I'll tell you that the velocity just after collision is going to be m1 v naught divided by m1 plus m2. So this is the velocity after they collide with each other. So what is the frequency after collision? What is the maximum displacement of the spring? So we talked about frequency already, and we know that when they're made of clay, they will collide and stick with each other. For some reason, the MCAT doesn't deem collisions necessary anymore, but you think about it, collisions are how chemical reactions happen. I think they assume that you guys have to know so many things with the new advent of biochem and sociology and psychology that they're sparing you from having to know collision. So that's why I gave you the final velocity after collision. Normally, I would make my students calculate that. So what is the frequency after collision? We've gone over frequency today for mass in a spring. And what is the maximum displacement of that spring? Oh. Another minute or so, maybe 2 more minutes total. Then we have to get started on this. This will be the 5th question of the day. And hopefully you guys remember that when you're dealing with a clay balls, you're dealing with an inelastic collision, and inelastic collisions, kinetic energy is not conserved. Just keep that in mind. Okay, I think that's enough time. So let's take a look at what is the frequency after collision. So what's the equation for frequency that we just learned today? One over 2 pi square root of what? Frequency over the mass, right? And so what's the mass? I mean, spring force over, or spring constant over the mass, right? What's the mass of the two objects after they collide? Yep. And that's it. That's your frequency. The elastic component over the restoring component over the inertial component, right? And that's your frequency after collision. And the second thing, so after they collide, these two objects are going to stick. And I told you that it's going to be moving with some velocity after the collision. So that means the kinetic energy at the end of the objects colliding problem becomes the new energy for the objects moving in the next energy conservation problem, because you're going to convert all that kinetic energy into potential energy. So we have 1/2 times the mass, which is m1 plus m2, because they're colliding, sticking with each other, times v squared, which is this whole thing, which is m1 v naught all over m1 plus m2 whole squared, right? That's going to be equal to 1/2 kx squared. So we want to find what x is, right? The maximum x. So we're going to cancel out the 1/2, divide by k to both sides, and then square root it, right? So x is simply m1 v naught all over square root of k m1 plus m2 in your system. And all we're doing is conserving energy from one point to another point. Notice I don't take it from the beginning, because during the collision event, I told you that using clay balls is an inelastic collision, which means we lose kinetic energy to the environment. So, but however, we can take the energy. Okay, how did I get the left side? 1/2 m1 plus m2 all over the velocity squared. I just use kinetic energy, right? After they collide with each other, the two masses are going to stick. m1 plus m2. And when they stick, it has some kinetic energy at the end of that collision experiment, right? So then I just use my 1/2 mv squared, and that's your kinetic energy. And then I converted all that kinetic energy to potential energy. And since the masses stick, we just add up the masses. Yeah, like physics is a lot easier than you guys have made it out to be. It's not the big bad boogeyman that everyone's so afraid of all the time. Right? It's literally, what are we doing? 1/2 mv squared. And then we set that equal to 1/2 kx squared. And so we just have to think about what we're conserving as we move from one point to the next point. We can be mindful of that. Okay. Okay. Last thing that we need to go over is our pendulum systems. So the first type of periodic motion was from oscillating blocks. The next type is from pendula or pendulums. So you think of a typical pendulum, it's being hung from a ceiling or top, has some length L, has some mass, creates an angle with the vertical. Right, so we know that this is mg, You can break this into components. This is mg cosine. This is usually mg sine. Okay. With pendulums, you just need to know what is comparing it with springs versus the pendula itself. You need to know what is the inertial component or restoring component. For springs, it's the spring force. For pendula, it's the gravity. You need to know what is the inertial component. It's unwillingness to change, right? For springs, it's mass. For inertia, it is your length of your lever arm. And the last one is your displacement from equilibrium. So it was displacement is a linear displacement for springs. For pendulum, it's an angular displacement theta. Okay. So from springs, we know that F is equal to 1 over 2 pi square root of K over M, the restoring component over the inertial component. Same thing for pendulums, 1 over 2 pi square root of the restoring component over the inertial component, the restoring component over the inertial component. Okay, restoring component is your gravity, and your inertial component is how long that length is. Period is the reciprocal of that, so 2 pi square root of M over K. Frequency is 2 pi square root of L over G. Okay. Sorry, this is period, not frequency. So this is the new one. The other way I like to remember this, there's a nice mnemonic to remember your springs and pendulum system. So when you think of springs, I think of like a whack-a-mole game. It goes up and down, up and down, up and down, up and down. So I remember the mnemonic whack 'em. I know Todd wants us to teach us the kick 'em and glide, but I personally like remembering whack 'em because I'd like to think of whack-a-mole. Sorry, this is K, not 8. It looks like an 8 when I draw my K's in cursive. Apologies. So when we whack them, it's omega is equal to the square root of K over M. So whack them, omega square root of K over M. And when I think of a pendula, it's like a wiggling, right? So think of it like a dog's tail that wags back and forth. So I think of the mnemonic wiggle. So omega is equal to the square root of G over L. Okay. And to find the linear, all you do is set that equal to 2 pi F or 2 pi F to find the translation back. Okay. This is L. This is M. Okay. So whack 'em and wiggle. This is basically your periodic motion. No gummy worms. I've stopped eating gummy worms. That was only during my college days. I can't eat gummy worms anymore. If I ate gummy worms now at like my age, I would be like a balloon. Like no joke. I can't like process like anything anymore. It sucks. By the way, when you guys are in your 20s, eat as much as you want. Like your metabolism's so great, it doesn't really matter. Pizza, buffets, whatever, right? Eat whatever you want. Once you hit your 30s, that's when it starts slowing down and it gets downhill. Yeah. So once you're in your 30s, it's like it slows down, and then once you're in your 40s, good lord, you might as well work. I literally go and work out for 4 hours to look the same, squishy. It was really sad. Remember, I would work I would work an hour when I was your guys' age, and I was like, in college and seniors. Like I work out an hour and I look like Adonis, and I was like, oh yeah, that's right, Michael B. Jordan, eat your heart out. But now I'm a fluffy, squishy gummy bear. All right. So with that said, we're done with periodic motion and torque. If you have questions, I'll be here now until 5. If you have questions from any of the things in the workbooks, I have them here. So feel free to ask, or any of the handouts. I can definitely go over them. Okay. Otherwise, I will see you guys. I have office hours on Thursday from 11 to 1. Email me if you can't make those, and we can try to set up another time that's available so that majority of the people can make it. But yes, I will see you guys on Wednesday this week, and we'll talk about some GChem there. I believe we're doing redox, but I'll look on the calendar again. If not, it's acid bases or something like that. Yes, Masa, feel free to send me questions in advance. If it's an easy thing, I'll answer it over email. If it's difficult, I will do it at office hours. Sometimes it's easier to draw out like the picture or show you over the video. But yes, feel free to email questions ahead of the time. Thank you. No worries. I got your message, Jonathan. Thank you. And you're such a good grandson.
Do we have time for questions now?
Yeah, we have
Okay.
an hour.
Perfect.
Yeah.
Would you be able to repeat the solution for question number 4, the spring question?
Sure. This spring question with this one, right?
Yeah, that one.
Okay, let's go through it. I'm gonna delete some of these things that we don't need, but let's go through all of it again. So we're starting with the energy we start with at the beginning, right? Which is all potential, which is 1/2. So PE initial. Let's delete all of this too, so we have more room. So initial energy that we have when we're at A is all potential. And then when we're at A over 2, we have potential plus kinetic, right? Who was I speaking to a second ago?
Yeah. Yes, I'm agreeing. Sorry, I was muted.
I was like, no worries. Yeah. You can leave it unmuted now. It's off
Sure,
sound.
yeah. Okay.
Everyone, like I feel if you want to chime in, right? I just needed to be quiet for class, but during office hours, like anyone and everyone can talk,
Mhm.
So I just want it to be informal versus like formal, right? So we want to find kinetic energy, right? But we don't have anything given to us in terms of like velocity and stuff like that. So we have to find everything in terms of potential energy. So kinetic energy final is potential energy initial minus potential energy final, right?
Can
I just subtract this
Yeah.
from,
Yeah.
right?
Mhm.
We're good?
Mhm.
So then we plug in the equation. So 1/2 K A squared, because that's the initial energy that we have at the beginning, minus 1/2 K A over 2 quantity squared. Right? This is the potential energy we have at this point.
Yeah. Okay. Yeah.
Potential energy here versus potential energy here, right?
Mhm.
So then we're subtracting the 2 to find kinetic energy. So 1/2 Ka squared minus 1/8 Ka squared, right? If we do the math out,
Squared, right?
right? Because this becomes A squared over 4. 2 squared is 4.
Mhm.
So 1/2 times 1/4 is 1/8. Cool.
Yeah.
And then we have to find the common denominator. Multiply top and bottom by 4. So we get 4/8 Ka squared.
Okay. So then 3/8.
Correct. And that's equal to your kinetic energy that we have in our system now at this point.
Mm-hmm.
But then my question was, what fraction of total energy is in kinetic at that point? So then we just divide the kinetic energy by the energy total, which is the energy we started with, right? Which is 1/2 Ka squared.
Why is E total 1/2 Ka squared?
What's the maximum energy that we had in our system? What we start with, right?
Okay. Mm-hmm. Yep.
Because in terms of conservation of energy, that's all we have, right? We don't get any more energy out of it.
Mm-hmm.
So then the Ka squared will cancel out. And then it's just arithmetic, right? 3/8 divided by 1/2 the same thing as 3/8 being multiplied by 2, right?
Mm-hmm. Okay, that makes sense. Thank you.
Yep, that's 3/4. Yep, no problem. And how do you pronounce your name?
My name is Charu, but it squished my first name and last name.
Yeah, that's what I figured because like just Jasmine. Yeah, I figured that was like your last name, so I figured it was Charu, but I didn't want to like butcher it. It could have been one name. You never know.
Yeah, no, I have a very long name.
No, I've seen longer. It's not that long. I've seen someone that have 15 characters as their first name.
Oh wow.
Yeah, and then 18 characters as their last name. I felt really bad for them, and I was like thinking of every standardized test where you had to bubble in your name, and I was like, "Oh my god, you want to shoot yourself, huh?" And he's like, "Yes, every time," and I'm like, "They're like, Mom, Dad, why did you make my first name almost as long as my last name?" And it was 18 characters. Like his name was Chichikarapol. He's Thai. Like I was like, and his Thai name is just as long as his last name. That's his family name, Chichikarapol. And I was just like, and we used to just call him Rob.
Oh no, that's terrible.
Yeah, like no, but he was like, I'd rather be called Rob because like I don't want people butchering my name.
Yeah, fair enough.
That, like everyone has a Starbucks name, right?
Yeah.
Just imagine having a Starbucks barista try to read that. But yeah, cool. Any other questions? Why is E total equal to 1/2 Ka squared again? Because that's what we start with, Michaela. So that's the maximum amount of energy that we have in our system.
So is that like the starting potential energy? I mean,
yeah, that's like
kinetic?
the total energy, right? Because when you let it go, is it going to gain any more energy? Think of the spring. You load it, right? And you pull it to get to that maximum point. And then when you let it go, are you pushing it still? No. The spring does all the stuff, right? And it's just going to bounce back and forth, back and forth, back and forth, which means it's going to convert from elastic potential to kinetic, back to elastic potential, then back to kinetic, and then so on and so forth.
Okay, I think I'm just confused because that's the equation for kinetic energy, right?
1/2 Ka squared is the equation for potential energy. I erased it, but yes.
Okay.
Yeah, but that's just the maximum energy you have in the system, right? And you notice that we equate it to PE plus KEF, right? That means that the total energy should be the same at any given point, right?
Okay.
Do you see?
Yeah,
so that
makes sense.
amount of energy is the same at any given point. So that energy doesn't change. It's just converted from one form or the other. So you think of an object that's dropping in air, it's doing the same thing, right? As that object is dropping, right? Let me see so I can see what's as that object is dropping, it's going from some potential energy state, so potential plus kinetic plus, except now there's more kinetic and less potential.
That makes sense.
At every given point, right? Until you get to equilibrium, which is now all kinetic and zero potential.
Okay.
Make sense?
Yeah.
Yes. Sorry, last week when I was teaching this, I assumed that you guys had taken it before. Like, I found out later that a lot of you had never taken this before. And so that's why I'm going to teach it and approach it differently. I had expectations last week. Okay. But yeah, I can answer in any and all questions if this is like the first time you guys are seeing this. Okay. And I know some other people are taking it concurrently too. So, Mo, you're awfully quiet today. Nandini, do you have any questions? If not, Charu, you can.
Yeah, I have another question.
Sure.
Example number 5.
Mhm.
You had a line that said you wrote KEI is equal to PE.
Yeah.
Can you explain why you set them to be equal?
Yeah. So, like we said, when a spring is getting compressed and expanded, right? At this point here, it's all kinetic, right? Because it has some velocity. That velocity is this V final that we have, that I gave you, right? And then we're going to move it to compress the spring. And the spring's going to be super compressed at this point, right? And that's the maximum displacement that you have from equilibrium, right? Because at this point, this is when X is equal to 0, right?
Yeah.
And so you compressed it. So then you're converting that kinetic energy to all potential energy.
You're converting that kinetic energy to all potential energy. Okay, yeah. Okay.
Yeah, the kinetic energy that you have after the collision, because when things collide, it's still going to keep on moving, right? Right. You all seen that like horrible commercial where cars get hit by the train and the train just keeps on going. Yeah, that's a horrible commercial, but it's like, yes, don't run like railroad crossings. Apparently that's a thing. I was like, why would people want to do that? I was like, I'm never playing chicken with something that's like, 8 tons. And you're barely like what? Like half a ton or a ton. With these cars nowadays, it's like maybe half a ton. Right? Does that make sense?
I think I haven't studied physics in 10 years, so I have to go back, I think, to the textbook.
Are you doing a post-bac right now, Charles?
I completed my undergrad in 2014 and I work in industry now, so it's been a while.
Yeah, I've basically been working ever since I graduated, so
That's relatable. Yeah.
It's if you don't do these things, it's just like in one ear out the other ear, right?
Yeah.
So it's like, just if you think about it, like think of a spring and you're pressing the spring. As you press the spring, right, you're loading up that energy. So all that energy that you had from movement, you're converting that energy into loaded energy that spring has, right? And then when it gets fully compressed, it bounces back.
Yeah.
So that's what's happening here. You're just loading up the energy that you have from movement to compress the spring.
Okay, that makes more sense.
Right.
Thank you.
Right. So it's like if you landed, like you jumped on the trampoline, right? What happens when you land on the trampoline? The trampoline compresses down and converts that kinetic energy you have, right? And causes you to come to a stop. And then what does it do? Boing. It shoots out, right? And it converts that potential energy back into kinetic energy. That's why you feel like, hey, I'm jumping just as high as what I did on the first one, right?
Okay, that's a good analogy, actually. Thank you.
Right. So this is kind of like that, like trampoline. So like I said, these are very all practical things, right? That's why you need to get familiar with this. So then when you do book 2, they're not practical things, right? When the hell are you going to deal with like sound? When the heck do you see light? When the heck do you see electromagnetic waves? You don't see any of those things, right? But you still have to use these same concepts, right? So when we're talking about springs, right, we can talk about them as forces, the vibration forces between atoms. When you think of lattice energy, when we talk about chemistry and physical chemistry and breaking things up to go from like, melting point to boiling point, you're breaking up these relative bonds between atoms, right? So you think of this elastic potential energy right? From vibration of the atoms when they vibrate. Think of like resonance and stuff like that.
Mhm.
Yeah, it's super practical, right?
True.
Cool. So what's happening is these atoms are vibrating just like this mass on the spring is vibrating, right? When you have sound hitting an object. So like all of this stuff, super practical. That's why I'm like with physics, like I love physics because it explains how chemistry works. It explains how the world works.
Mhm.
And if you actually put time into it and like try to really understand it, then you can start explaining how the world works, like from the atom inwards out,
Mm.
right? Because if you think about it, when we talk about Coulomb's law and electrostatic forces, that's how atoms are bound together, right? Opposites attract, likes repel, that kind of deal,
True.
right? That's what's keeping an atom together, right? The nucleus of protons attracting the orbiting electrons as it goes around in all these weird different shells, the S, the P, the D's, and the F's, right? And then trying to keep them balanced based on the Coulombic force of attraction that's between them, right? And then getting another atom's close enough so that it can attract its electrons to want to bind to that nucleus of the first atom's nucleus, right? The protons from the first atom.
Right.
Make sense?
Mhm.
Cool. So it's very applicable, but the idea of forces and attraction and repulsion and conservation of energy, these are all applicable ideas because when you think about it, when we think about it in the macro scale, like you're talking about like things vibrating, things breaking, giving off heat, energy, entropy, all those things that like those are all macroscopic properties. The microscopic is just this vibration using a spring. Right? And we model those bonds like these springs. Cool. Cool. Anything else? You got me for an hour, Charu. So if you want to use it.
I'm gonna drop. I think those are all my questions for today. Thank you.
Cool. Yep.
Bye.
I think Ben's out with his grandmother, and I don't know if Mo's there because he was very quiet today.